Hey everyone, so in today's video we're going to go over some introductory statistics, and we're just going to cover the basics and how we can use programming, specifically Python, and Pandas and SciPy are the ones we're going to focus on today, and how we can quickly perform like descriptive statistics, like the mean, median, standard deviation. We talked about that a little bit in the previous lesson, but we're going to go a little bit deeper into that, and we're going to talk about various statistical tests, such as a t-test or an ANOVA or correlation analysis, and how we can quickly do those if we have our data in Pandas, or if we're using SciPy to do that as well. We're going to talk a little bit about overlays, a little bit more using matplotlib than what we did before, such as like mean lines in box plots and some regression lines. We'll talk about how we can add those, and how we can just create an even more publication ready figure to analyze the data that we talked about collecting last week. Okay, so the first thing that we're going to get into is just our basic descriptive statistics, such as our mean and median. We can also do mode as well, just gives you the most frequently repeated number in our data set. And then we're going to talk a little bit about how standard deviation can help us determine which one we might want to use. So we're going to go ahead and use pandas like we did before. So import pandas as PD. Not pandas. There we go. Okay, and then we're gonna go ahead and get some data. So we'll just say data set 1 equals PD series. We could also make it a data frame if we wanted to. Okay, 1, 2, 3, 4, 5. Okay, and then we're gonna go ahead and create our data 2 as the same thing, but I'm going to give it an outlier. Instead of 5, we're going to make it 100. Okay, so we want to look at these two data sets and see, okay, for data 1 and data 2, which one is going to be the most efficient way of describing the general trend of this data set. So we could start by just saying, we'll say mean 1, then we can say median 1. Okay, and then for each of these, we're going to say data 1 dot mean, and for this one, oh, I put an extra underscore. We'll say data 1 dot median. Okay, so now we can print mean, and then we'll do median. Okay, and let me put a new line break there. Okay, so if we did this, we're just looking at data set 1. We can see the mean is 3 and the median is 3. So they're both the same. In this case, it doesn't matter which one we choose because it's going to give us the same kind of description of our data set. But what if we come here and we're going to copy all of this? Okay, and we're going to say this was data set 1, and this one will change to data set 2. Okay, and then on this one, we're just going to change all these out for a 2. And so I'm going to select this. I'm going to do Control F to find, and I'm going to replace all of the ones with a 2. So this is a quick shortcut that we can do. And I'm just going to go 1, 2, 3, 4 until it's all done, and then I'm going to stop. Take that little drop down again and hit X so I don't accidentally change some of these other ones. So that's a really quick way for you to go through and switch these out. Okay, so we're going to save that, and we're going to go ahead and run. And for data set 1, we had 3 and 3, but for data set 2, we have 22 and 3. Okay, so in this case, I'm going to put a little extra line there so it looks a little better. So in this case, our mean and our median are different for data set 2. So to understand which one is more descriptive of our data, we could look at the data, we could plot the data, or we could calculate a standard deviation to see how spread out is the data away from that mean. And if that standard deviation is very large, we probably would like to use a median instead to get rid of any of those outliers. Okay, so the way we do that is we can come here and we can say standard 2 for standard deviation is going to be dataset2.std standard deviation. Okay, and then we're going to come here and we will say standard deviation stand2. Okay, and then we can print this. So as you can see, that standard deviation is very, very large compared to our mean being 22. The standard deviation is 43. So when your standard deviation is larger than the difference in your data set, there are some calculations you can use for whether it's a significant outlier. Boxplot specifically will do this automatically for you. And in this case, it's called a quartile. So if we take our data set and we break it up into fourths instead of into halves, so when we break it up into half, then that's how we get our median of right here at 3. If we were to break it up into fourths, and we would say, okay, well, this is a fourth of our data, this is a fourth of our data, this is another fourth, and then this is another fourth of the data. And it generates these numbers. If you have a larger data set, this makes more sense. And then if the range between this fourth of your data set, if your standard deviation is larger than that 1/4 range, that inner quartile range, so the 50% of your data set here in the middle, then typically it will be considered as an outlier if it's more than twice that inner quartile range from the end of another data set. And you can go into more of the details of how that's calculated, but the good thing about with using pandas, and we're going to use SciPy in just a minute, is you can generate these outliers automatically without having to go through the process of calculating every single data point. So in our case, we only have 5 data points, but it would be a lot more complicated if, say, we had like 5,000 or 50,000 data points. We wouldn't want to go through and see, well, which numbers are outliers in our data. Okay, so let's go ahead, and from here we could say, like, we could do some logic. We could say if the standard deviation 2 is greater than our mean, then maybe we want to print our median instead of printing the, let's go here. So instead of printing the mean, so we'll do this, and then we can say if it is, or we can just change this to an else, and then we can print mean. Okay. So then, of course, in this case, it's going to print the median because the standard deviation is so large. Okay, so let's move on. The next thing that we're going to look at is going to be a p-value. So we can look at these two data sets, and although they kind of look the same, that mean was different. It was 3 versus like the 22 for the data set 2. So if I were to ask you, are these two data sets the same, or are they significantly different? And this is how, like, let's say you have 2 different groups in your data that you're collecting from, and one is like a control group. So they didn't have any kind of like intervention, and then you had an actual test group that had some kind of intervention. It could be like a behavioral intervention, a drug, or maybe you're testing to see if there's an effect of certain conditions that they have that this other group does not have. And you want to know, okay, is their outcomes or their results, that data you collected on them, is it different? So in this case, I would say, well, it kind of seems different because we have this 100 out here, and this group didn't have the 100. And the means are very different. One was 3, one was 22. So maybe I could say, yeah, they're different. But maybe somebody else would say, well, no, they're not different because the medians are exactly the same. So how would we, in a scientific context, we have to have our statistics to back up our claims that we say. So we use what's called a p-value. And a p-value helps us determine, and this is like an accepted way of determining whether or not these two groups are the same or if they're different. And the way it does this is it says, okay, well, if I were to randomly select from either of these two groups, what is the chance that just by randomness, so if I were to just randomly flip a coin and that coin would be a heads or a tails, what's the chance of that being just random data point that was just thrown in to your data set, or those two just randomly being selected from the same data set. It gets a lot more complicated than that. When you take a full statistics class, then you'll kind of understand the differences there. But in general, it says there is a 95% confidence interval that this significance or this relationship is not due to chance. And the way we do this is by calculating that p-value. And the p-value, if it's less than 0.05, then we can say that it's significant. If it's greater than 0.05, so even if it's 0.06 or 0.1 or whatever number is greater than 0.05, then we can't confidently say that these two data sets are different. Then they're technically, chance-wise, they could be the same data set. We just don't have enough samples to know that they're different, or they just appear to have this trend of being different, but in reality, they could be sampled from the exact same group of data, just two subset selections of the same data set. So the way we can calculate this using code, we don't have to know the super long formula and look at every single data point and calculate this difference from the mean. And that's how it's calculated. You can look up a little more on the specifics of how a p-value is calculated. It's a lot of adding and subtracting and averaging a whole bunch of numbers together and a lot of differences from the mean. But a computer can do that for you in seconds. And we're going to use a library called SciPy in order to do this. So at the top of our script, we're going to go ahead and say from SciPy. Oh, we don't need a... Okay, so from SciPy import stats. Okay, so we're going to come down here and we're just going to use R2 that we have here. And we're going to create a t-statistic and a p-value. We'll talk a little bit more about what the t-statistic is in a minute. And we're going to say stats because that's what we imported SciPy as, or the SciPy stats as. And we're going to say t-test for t-test, which is how we're generating the differences between two large data sets. So we have two full data sets, and we're trying to calculate the difference between these two data sets. IND. This is just the function name. And then we're going to give it our data that we want it to, our data sets that we want it to compare. So in this case, we have data set 1 and data set 2. Now, if that p-value is less than, or we could say less than or equal to 0.05, let's just say less than, because usually it's going to be a decimal. Then we're going to say print the data sets are significant. Different. Okay, and then we'll say with our little curly bracket, and we'll say p-val. All right, and we'll say p. Usually use a lowercase p for p-value. Okay, and then we'll put that p-value there in the bracket. And don't forget, if you're using that inline literal, string literal, you need to put an F at the beginning of it. So it's just going to say the data sets are significantly different. Okay, and then we're going to copy this. And then we'll say else. So if it's not, if it's greater than 0.05, we'll say the data sets are not significantly different, and then we'll print the p-value as well. So we think that this data set is different because one has 100 and the means were completely different. But when we look at all of the data points within our data set, we might be surprised by what we find. So we're going to go ahead and run this. And when we do, we can see the data sets are not significantly different because our p-value is 0.35 or 0.36 if we average. So if our p-value had been less than 0.05, then we could say that it was significant. So what we're going to do is we're going to take all of this and we're going to copy it, and we're going to run a different one. So I'm going to, let's go ahead and comment out all of our print statements because we don't need all of these in our terminal. It's kind of making it messy to read down here. And we're going to get 2 new data sets. So we're just copying the same stuff we did up here. We don't need that mean, median, and mode anymore. Our descriptive statistics, we're going to do some more significance testing. Okay, so we're going to say we have data set 3, data set 4, and let's say instead of, we have 1, 2, 3.45, and let's say we have all of the, oops, didn't mean to do that. Okay, and then we're going to come here, 96, 97, 98, 99, 100. Okay, so these are very different data sets. So one's the first 5 numbers and then the last 5 numbers. So ideally, these two we would think would be very different, but in order to say that, we need to test the actual significance. So we're going to come here and we're going to run, but this time we're going to run it with data set 3 and 4. And you can see our p-value is 1.68 to the negative 13. So it's 0.000013 decimal places out and then 168. So they are definitely significantly different. And you can see where if that p-value is less than our number threshold that we're setting it at, 0.05 is the most common significance test, then we can say with confidence that these are 2 different data sets. Or let's say that these were the scores of somebody in group A and these were the scores of somebody in group B. Well, you can tell there's definitely a difference between that that data score that we have in these 2 groups. So it's very important to know how to do a basic p-value or a basic t-test to get that p-value. Okay, so that is a p-value. So one last thing before we move on that is important to note. So these data sets are relatively small. We only have 5 data points in each of these. So we can also analyze the t-statistic that is generated from this t-test from SciPy. And in general, a larger t-statistic, this number that it gives you out, typically will give you a smaller p-value, meaning that it's more significant. So like when we compared our data set 3 and data set 4, while sometimes like if you have high variability in your data, so let's say that this data was 1 through, or like 45 through 50, and then data set 4 was like 1 to 100. So the averages are both going to be 50, but because one has a larger variability, a larger spread, that standard deviation is bigger. Sometimes that larger variability can reduce your t-statistic and increase your p-value, kind of like when we had in that data set 1 and 2 here, like the non-significance, because in data set 1 and 2 we had 1 through 5, and then 1 through 100, we had a much larger standard deviation or variability range there. But sometimes also having small samples, because these are very small data sets, it can also reduce your t-statistic because that variability is much larger for each individual data point compared to the mean between the 2. So like when we go a little bit further into this, if you there are some things called degrees of freedom that you calculate, and typically a degrees of freedom is going to be the number of data points in your data set minus 1, or n minus 1 is a common terminology for that. So in our case, we have 5 data points in our data set, so our degrees of freedom would only be 4, which is very small for degrees of freedom in this case. So as we're going through and looking at our data, we want to make sure we analyze more than just the mean, the median, and then the p-value. Sometimes we need to look at what is the size of our data to know if it's significant, because we could have a very good p-value or a very significant p-value, but if we only have 5 or 6 data points, it may not be as confident as we would like. And sometimes you will find publications that they will post their p-value, but they won't tell you their degrees of freedom. They won't tell you some of these other statistics that are important to knowing whether or not their data is actually strong enough statistically, or if they just got a number and then they published on it. So I highly recommend taking a full stats class if you haven't already, or maybe if you have, go and refresh it before you start analyzing your actual data, just to make sure that what you're publishing as significant is actually significant and you're not just calculating a value and saying it's less than 0.05 and reporting that. Now, there is still something to say about that, but you just need to understand the difference there. Okay, so now let's go ahead and move on. Okay, so another way that we could generate just these basic descriptive statistics is by using an actual data set that we have, and we can read it in just like we did. So we generated our data set here using a Pandas data frame. I'm not going to walk through this specifically, but we could do the same thing if we read the data from a file. So if we take like that task data that we had in the previous lesson and we could read it from like a CSV or from an Excel sheet, depending on how we save that data, or TXT, and read it in line by line. And we could generate the mean, median, and the standard deviation of that data set, and we could just plot this. So this is going to be very helpful for your assignment for today, and you're just going to basically do this exact thing. You're going to read in the data. You could do this with the data that you collected from your task in the previous lessons if you wanted to just get some general statistics for it. And then you can print this, and the most important thing here is you can say df.describe. So we could generate all of these by hand by calculating mean, median, and mode, or we could just say df.describe, and df.describe is going to give you a summary for all of the columns that you have in your data set, and it's just a much quicker way of doing this instead of doing it manually for every single column over and over and over again. So you'll just copy this line right here, and it's very useful. So just a shortcut, and this is the benefits of using specific libraries that have already been pre-written for us. Okay, so now let's get into a little bit of a different type of significance testing. So before, we just asked the question, well, was dataset 1 and dataset 2 or 3 and 4, were they the same dataset, or were they significantly different? And that is essentially a hypothesis that we're testing. We're saying, okay, our datasets are the same. And then we're going to test, is that true or not? We're going to try to disprove it. So we're going to say, okay, well, I want to try to see if the data sets are not the same, which is what we call the null hypothesis. So it's the opposite of what you're trying to test. You're going to try to disprove your hypothesis by confirming the opposite of what you're checking. So we can test this hypothesis, or whatever hypothesis that we're trying to prove, or disprove null hypothesis, or prove the null hypothesis. So by doing this, if we have two groups, then we can do the t-test, just like we did in all of these. So this t-statistic, it generated a t-test, it calculated dataset 1, dataset 2, do that t-test indicator, and then we can see if it's significant looking at our t-statistic and our p-value. But what if we have multiple different groups? So instead of having a normal two simple data sets, what if we have like 4 or 5 different groups of data set? Then we can do what's called an ANOVA. So an ANOVA will compare, if we do like a one-way ANOVA, we can compare between multiple different groups. So we can't just do 2 anymore. Let's say we have 3. We can't do a t-test with 3 different ones. We'd have to do a t-test between each of the different pairs and then compare them. An ANOVA will compare across all of the groups. So let's say we want to check dataset 2, 3, and 4 to see if they're significant. Okay, so or if they're significantly different. And we might have multiple different conditions that we're testing, and we want to see is there any difference between all of these different groups. And the way we do this is we have an F statistic instead of a T statistic, because we're performing an ANOVA, and we're going to still have our p-value to be able to test that significance. And then we'll say stats.f_one way for a one-way ANOVA. We could also do a two-way ANOVA, but we're not going to get into that for this class. Okay, and then we're going to come up here and look at the data sets that we want to compare. So we want to do data 2, 3, and 4. So we're going to say data set 2, data 3, and then data 4. So we're testing 3 different groups, and we're going to go print ANOVA, and then we'll give it the F statistic. Okay, so let's do F stat. Now remember, these are very large numbers, so if we want to actually print them in the proper format, we can round it to 2 decimal places, and then we'll say the p-value is p-val, and then again we can round it. So typically you want to round the p-value to at least 3 decimal places because we're testing for 0.05 significance. So if it was like 0.01, it would show round as 0.0. So if we do 3 decimal places, it gives us just that extra decimal place just to show if it's like a little further. You always want to go 1 more than whatever your test is checking for. Okay, and then don't forget to put that F string literal at the beginning if you're going to put variables inline. Okay, so we're going to save this, make sure we don't have any other print statements here, and we're going to go ahead and run. And you can see that our ANOVA came back with a p-value of 0.00. Okay, so and don't forget to put that F here so that it actually rounds it. Okay, so you would have a p-value of 0.000. So in this case, when it's 0.000, we might want to come in here and say like, okay, well, let's do 4. And then come in here and then we'll be able to see, okay, 0.0002. So this is very, very significant that these 3 groups are very different from one another. And then you can go from there. So now we know we have variability among these, but we might still want to go in and check each condition against each other using that t-test. And then that's where we can say, okay, well, these are very significant. So that's why all 3 of them together are very different. But maybe this one and this one, remember, it was not significantly different because data set 3 is the same as data set 1 in this case. Okay, so another test that we can do is a correlation analysis. And our correlation analysis is just going to look at any relationships that we have between some metric that we're measuring and some other metric that we have. So you can, let's say that we have these 2 data sets. So we know that these are very, very different data sets. So if these were both our scores, then they're completely different because these scores are at the very low end of, these are at the very high end. But what if this is our time series? So this was trial 1, trial 2, trial 3, trial 4, trial 5, and this was the score that we got. So we started in trial 1, we made a 96. The second time we did it, we had a 97, and then a 98, 99. So you can see that there's something happening here. But even though these are, if they were the same type of data, they would be different. But if this one is dependent if this data set 4 is dependent on data set 3, there is some correlation between these 2 variables. So we know that there's a pattern and they each increase. As this increases, this is also increasing. There is some kind of positive correlation. As one goes up, the other one goes up. Negative would be as one goes up, the other goes down. So if we wanted to test to see if there is a correlation or some kind of trend between these 2 data sets, we can do this doing a correlation analysis. So to do this, we just type correlation, so whatever you want to name it. We're going to, again, have our p-value to just test the significance. So that correlation is going to tell you what is the correlation. Is it a positive correlation, a negative correlation, or no correlation at all? So if it's like there's nothing, it could have a significant no correlation. Okay, so we can come here and we're going to do stats.Pearson. So this is a type of correlation. It's one of the more common ones. It's a Pearson correlation, and it's just generating all of the data points and calculating their difference from the average for each of them. It's comparing each two data points to each other and calculating if there is a significance between each of those data points compared to each other data point in the set. All right, so then we're going to give it data 3, data 4, because we want to test, is there a correlation between this and this? Okay, and then to do this, we're going to print, and we'll say correlation. We're going to give it that correlation coefficient, which is the R stat. Okay, so we'll do correlation coefficient. We're going to round that. And then we're going to give it the p-value. Okay, and then we'll also type in that p-val and make sure to round that to 3 decimal places. Make sure we close all of that out, and we don't have any other print statements. No, we're good here, so we're going to go ahead and run. And when we run, we see that there is a correlation of 1. That is one of the strongest correlations you can have, because these are exactly 1-to-1 ratios. This goes up, this goes up. And it is a positive number, meaning that we have a positive correlation. One goes up, the other goes up, or one goes down, the other goes down. Negative correlation would be they go in different directions. So as this one goes up, this one goes down, or vice versa. As this goes down, then this one would go up. So we have a positive correlation, and our p-value is 0 because there is an exact correlation here. So if we were to come in here, let's just change it just a little bit. So let's say 102.46. So now it's not an exact correlation. Yeah, so let's go ahead and save that and run. And you can see now our correlation went down just a little bit, but it's still significant for that correlation. And then there are thresholds that people will typically accept for that correlation value. But in general, the larger, the closer that correlation number is to a positive or negative 1, the more correlated your data set is. And as long as that is significant, then you have a correlation. So this R statistic could be 0.55. That is a positive number. If it's not 0, if it's farther, the further it is away from 0, the stronger the correlation you have. But if it is 0.55 and your p-value is less than 0.05, you still have a positive correlation. It does not have to be within that 95% for your correlation coefficient, this R value. You're really just looking at this p-value for significance, and then this is what you can make as your conclusion. So if you just want to say there is a positive correlation, your correlation coefficient could be 0.1. And then if that is significant, then it's a weak positive correlation because it's a very low correlation coefficient, R. But if this is significant, then you still technically have a positive correlation. So you have to look at both that correlation coefficient and the p-value, just like we had to do with the t-statistic for the previous test. Okay, so hopefully that all made sense. That's just an introduction to statistics. There are a lot more details and nuances that you can go into, and a lot of other tests you can do, and you definitely need to take a full statistics class. But those are some of the most common things that you're going to see in papers or that you're going to be doing on your data set. And then knowing how to implement that quickly in Python or in whatever language you're using is very important. And then once you learn these new techniques, then usually there is already, so as you can see, we use t-test and then Pearson correlation. We're just simple functions that are already preloaded into this SciPy stats. There are hundreds and hundreds of others. And once you learn what those other tests are, if you need to do it, you can usually just go onto the documentation of SciPy and you can see the exact function name that you need to call to run that test on your data. Just make sure that you are using the correct data test for your data, and you're analyzing all the numbers that you get out of that, and you publish all of those numbers. You usually want to put all of those onto your graph, and that actually kind of leads us to our next step. Okay, so in the previous lessons, we talked a little bit about using Matplotlib to plot our data. We put some overlays on it. We showed like the mean lines, and we want to add a little bit to that. And now that we know how to calculate p-values and significance testing, we want to also add that p-value and significance testing results, like the actual p-value, and display that onto our graph. So to do this, let's go back into our lesson 5, and I'm going to copy over our data. I think I already have it in here. Yes, so I already have the data in lesson 6. And then let's also go to our Python script that we had from before, and we can just go ahead and copy in that same code that we used to read our data that we had before into a Pandas data frame. So let's take all of this. Actually, let's come in here to lesson 6 to keep it a little cleaner. And we're going to say lesson 6 video part 2. That way we can just have a clean slate to start back on. Okay, so remember we are using pandas and we're going to use some SciPy, so we need to make sure we copy and paste that over into our script. Okay, and we're going to read data xlsx, which is already in the same folder that we're working in, so just make sure all that's good. And I'm going to close out our old script that we were working with and the previous lesson. Okay. Okay, and then we can also pull up our data, which is a good idea. If we're working with the data, we want to remind ourselves what the titles were for the top of that data. So we can also come in here and we can say that values is the value. Double clicking will select the whole word. Triple clicking will select the whole line for you in VS Code. Okay, so we want the values, we want the ID, and then the responses here. Okay, so now we have this data. We're going to come in here, and first thing, we're just going to create a box plot of the data that we want. So within specific conditions that we have based on whatever we're using as the response. So in the response kind, we had keys 1, 2, and 3. We could replace some of this data or remove it. And so for today's purposes, let's just come in here and we're gonna replace some of these. Okay, so we could do this manually if we wanted to. Okay, so we have 1, 2, 3, 4, 5. All right, so we'll say that's 6 here. Okay, and then now we have all of our data filled. We could have done this. Normally you don't want to go in and manually mess with your data, but we're just going to say this was our original data that we're working with, so we don't have to deal with invalids and stuff. We've already cleaned our data. Okay, so now we have all of our data in here. We could read this in and we can print it just to make sure that we've got the data frame imported the way that it should be, but we're going to assume we did all of that right. And we're going to go ahead and create a figure, plot figure, and we're going to give it a fixed size just so we can load things into it properly and it'll be the right dimensions for us. This isn't an option. And then also make sure we import our matplotlib. We're going to be using plots. Okay, and then we can generate just a simple box plot. So a box plot is going to show us a little a square, and it's going to have that median, and it's going to have those quartiles, and it's going to have the little whiskers on the side that reach to the max and mins of our data set, and any outliers we might have will be little asterisks on the outside of those. And it'll calculate all of this for us. So plot, box plot, and then we're going to give it the conditions that we have. So in this case, we need to pull out specific conditions. So in our responses, remember it could be key 1, key 2, or key 3. And we'll copy this right here. And we're just going to come in here and we're going to write condition. So we'll say condition 1 is if data frame, and then we'll do response equals whatever value we want to set it at. So we're going to say key 1, and then we also had key 1, key 2. There's no spaces, so make sure we do that. Then we're going to give it the value, for example. Okay, so we'll say that we're going to return the values based on the keys that we had. And then in this case, we don't need the responses as a separate data set. That's if you wanted to loop through. So we can just do this quickly for condition 1, condition 2, and condition 3, meaning if it's condition key 1, key 2, or key 3, and make sure you change your variable names. So if this is a little confusing, go back to the previous lesson 5, and we talk about this a little bit more of how we can read in with specific conditions. Okay, so I'm going to go ahead and I'll leave this here. We don't really need these right here. These are just for further analysis in the future. So to go through and create this box plot, we want to take each of these conditions and plot those values on our graph separately. So they're going to be separated by which key. So it's going to take all of the data in this table, all the values, and separate them out into groups based on this column C, and plot that with all of the descriptive statistics that we want for each of those categories. Okay, so we're going to do condition 1, condition 2, and then condition 3. Okay, and then we can go ahead and give it labels too if we want to, just so that when we put our figure legend on there later, it will make it easier for us. And we can say key 1, key 2, key 3. And this can be any category that you have that has some categorical definition. So we have keys as our categories, but it could be any kind. It could be numbers. It could be some kind of group. It could be a threshold of certain scores. You can break it up into if it's between a certain range and then put it into that category, however you wanted to do it that way. Okay, so now we have this, and we're just going to come down here. We're going to go ahead and add the rest of the stuff. So plt.show, just so we can go ahead and see what's happening. We're going to add a lot of stuff in the middle between here, but remember, our plot will not show if we do not have that plot.show on there. Okay, and we're going to run. And give it just a second. Oh, I use the word fig. Oh, fig size, not fig. All right. And then we're going to come here and we're going to run. And as you can see, it's taken all of our data, it's separated up into the 3 groups, and we have all of them listed right here, nice and pretty on top of our graph. So for the rest of this, once you get that box plot, that's pretty much showing all of your data categorized. We may want to put that p-value on top of it that we generated before. So if we come back over here and look at since we closed that out already, let's look at how we calculated the p-value for specific data sets that we had. So let's say we want to do a p-value significance between each individual pair of these categories. So maybe we want to do key 1 to key 2, then key 2 to key 3. We could test each of these individually using a t-test, or we could do maybe an ANOVA, and we want to plot that on top of our graph. And the way we'll come in here, we'll take and copy this over, and we're going to generate, oops, there we go. Okay, so we can say our p-value for our F statistic, and instead of data 1, 2, 3, we're going to use condition 1, condition 2, and condition 3 for each of those that we have. And we're just looking at that value set again. And we can print this in our terminal, but we also want to show this on our graph as well. And we can give it like a label title if we wanted to. We can do all of these other different things just to plot it on top of our graph. And I actually have a couple of different things that I'm going to show you. So I have it in our assignment. Let's see. We have it right here. I'm going to just pull this up so you can kind of see. We have a couple of different ways where I've added a jitter. There's a couple of things that we can add our data points on top of our box plot, so it's a little easier for us to see. Let me come here and we're going to copy this over. We're going to have some custom colors, so I'll kind of go through what everything is doing here. Okay, so we already put our box plot here with all of our data, And within this, we need to use NumPy in order to do some random. So we're going to say import NumPy as NP, and we're going to be able to have those randomizations that we have in here. And for our box plot, we're going to assign it a variable box just so we can do some stuff to it and change the colors in a minute. So we're going to have teal, lime green, and we'll do orange for our 3 condition colors. And this is just setting custom colors to be able to plot these conditions. And we're going to say everything within that condition is going to have that color. And we're going to change the alpha, which is a little bit of a transparent color. So this is a little more advanced plotting method for when we're putting everything on our graph and trying to show everything. And then in order to plot the actual XY data sets, we could just put them all there, and then all of the X's would be just 1, 2, or 3 for key 1, key 2, key 3. But we know that some of these may have the same key 1, 2, 3 for their values over here. So if 2 of these were the same, which we know because we copied and pasted this one and this one, then they would just be the same point on top of each other. And we want to give it a little bit of a scatter so we can visually see all of the data points. And the way we do that is just generating a simple random. And then instead of map scores, we're going to have our jittered around each of our values that we have here. So we're going to do condition 1, and then we can have condition 2. And then, so this would be X condition 1, and then we'd have X for condition 2. And you can skip through this portion until we get to adding the p-value if you're not interested in making it look pretty. Okay, and we're going to do this condition 3. So all we're doing is we're going to each of these different sets, and we're going to do 1, 2, and 3 for our X values for where our points are on our graph for each of these. So when we have labeled data, our X is just going to be 1, 2, and 3. Or if we had 5 categories, it would be 1, 2, 3, 4, and 5 for where the X condition is, because there's no actual number for our X axis there. Okay, and then X equals 3 for that key 3. So this is just allowing us to add those scatter points, and we're going to actually add the scatter points on there. And then we're going to come here and we're going to have condition 1. So this is taking those X coordinates that we just scattered around that vertical line of X so that they're left and right a little bit. And then we're going to give that a color. We're using teal, lime green, and orange. So we're going to keep these the same. And I'm going to do condition 2. And then we'll do condition 2 here. And we're going to do the same thing again, but this time we're going to do condition 3. Okay, and then we're going to say the label for this one was key 1. The label for this one was if they did key 2. And then the label for this one is key 3. Okay, and then these are some other little variables that you can do in here. Again, alpha is just the transparency of that color. And we're going to use orange for that last color. So all I'm doing here is adding the data points on top of this box plot and changing a little bit of the color. So I'm going to move this statistical test thing down here. Okay, so now that we have this statistical test that we're doing, so this is do stats test between these 3 conditions, then we can now add that stats test to our graph as well on top of all this color that we added. And we're going to tell it where we want it. So this is just our X and our Y. We can move that around later in a minute. Right now I'm just putting it right there between the 1 and the 2. You can put it at the far right aligned with the HA line. And then it's we're going to actually go and we're going to change this to 3.5 because we have 1, 2, and 3. It's going to be on the very bottom right of our graph. Okay, and we're giving it that p-value. We're rounding the p-value and we're putting it in the corner. We could add any other text we wanted to and say like the results are significant or the results are not significant. It really doesn't matter what you put here. But we do, because we added these labels, we do need to do plot legend. And it's a good idea to go ahead and give it some of these other labels. So we're just going to say value versus key pressed. Okay, so that we have the key pressed for our X, and then we have the value that we're plotting on our Y. And then in this case, we don't know what that value is, so we're just going to say arbitrary units maybe. Or if you knew what it was, then you could put that. So this is just what is the units of the values that are in this category here. And then this Y label, what's going across here, oops, is going to be our key. We'll just say key here. Okay, and we're going to hit save. And as long as we typed everything right, it should work for us. It should read our data in. Oh, hold on. We don't want set face color. Let's see. Where is our face color? And we have patch. Oh, okay. So in order to use this patch here, we're going to actually have to do one additional thing here. We have to allow custom colors to happen in that box plot. So this is just a copy and pasting if you wanted to do this custom color. So I'm going to add this. There we go. Make sure we add that extra comma. So we're just adding all of these labels. The patch true is allowing this next part of code to work. So if you skipped this color point part, then you can just remove that line. Okay, so now let's run and see if we typed it out right this time. There we go. Okay, so now we have our colors, and you can see we plotted our data points on top of our box plot. And now we have our legend over here. We can move where our legend goes. Remember, I told you the legend will kind of find the best place that it wants to go, but you can force it to be left, right, bottom, and everything. And our p-value did not plot because we plotted it at a value of 3.5, which would be over here, but 5. So it's way up here above our graph. So if we look at our x-axis, our y-axis is only 1.4 to 2.2. So let's put it right here at 1.4 instead of 5. We're just telling it where we want that to save. And make sure you close that before you try to run it again, or it will sit there indefinitely. And you can see there's our p-value. So maybe let's actually move it up to 2.2. We can just move it around by telling it the coordinates that we want it to go to over and over, and then run it again. And there we go. So this is the p-value, and you can see the p-value is very large. So there is no significant difference between all of these when we did an ANOVA. And you would want to say your ANOVA p-value is this. Or you want to put like some brackets, and you can say between key 1 and key 2, put some little square brackets here, and then put an asterisk or a star. And then you can say that, okay, well, even though all 3 of them together were not significantly different, then between this one and this one, maybe these are significantly different, or this one and this one are significantly different. Our data set does not look different, but in order to do that statistics test, then you could confidently say that they don't look different, and statistically they are not different from each other. Okay. So that's pretty much it for today's lesson. I know there was a lot here at the end, and I'm adding in a couple of little more advanced techniques as we're plotting this. So if you want to stay simple, you can remove all of this right here, and then just go back to that simple box plot and just add that text on your graph. Or if you want to go a little more complicated in your assignment, then you can change the color. You can add your data points on top of it. You can move that text around so it's not just randomly on screen. You can tell it exactly where you want it to go. You can put a box around it. You can add additional text. You can really kind of go wherever you want from here, and get it as complicated as you want. As long as you know how to do this statistical test, you know how to do an ANOVA, or you know how to do a simple t-test or correlation analysis based on what you're trying to test, and be able to display that on the graph. That's really the goal of today's lesson, is just to have an introduction of how you would show that. Okay, I'll let you guys get working on the assignment, and let me know if you have any questions or problems.